Thank you everyone for joining us for today's series of NAPA Education, the Lunch and Learn series. And so today's topic is going to be one of my favorite ones to cover. It's ADAS calibration tips and techniques. And prior to this job as a trainer and developer, I actually was an ADAS calibration specialist. And along with that comes a lot of different tips and techniques and also things that we can get wrong in the process. And I want to try to help you out as much as possible today, kind of explain these systems and also walk you through some different tips that I've learned over the course of the years prior to doing this. So with that, let's get rolling. Again, today's topic is on ADAS calibration tips and techniques. And so with that, we're going to get into the presentation and go through all of the different slides that we're going to cover and try to really show you some different methods. And we're also going to walk you through all of the tooling required for this process. The first question that we have to ask ourselves is, what is ADAS? And if we're unfamiliar with these systems, we definitely need to know what the description is. So ADAS stands for Advanced Driver Assistance Systems. And essentially, the reason why we've got these systems are to try to keep the driver safe. We want to avoid collisions if at all possible, and these systems aid in doing so. Now, we've actually already got driver assistance systems on the vehicle, and some of these we may not really consider because we're just kind of used to these systems already. Some of these would be things as simple as, well, now it's as simple as electric power steering, traction control systems. Even our cruise control is a driver assistance system. And one other one would be supplemental restraints. Now, all of this data that we see on the right-hand side of the screen, this is all networked information between all of these various modules. And so this is already kind of integrated into the vehicles as we're driving them, to present day. The addition of ADAS is going to add a variety of different sensors along with this. So we're going to already use the information that we had on the vehicle prior to this, and we're going to just add some other things to it. So we may be utilizing things such as short range or long range front radars. We could be using side radars on the back of the vehicle for blind spot or any side object detection. We also are going to be utilizing a series of cameras. This is going to be to see where we're at in location to the lanes that we're driving in, and also for parking lot maneuvers. And we also have a variety of distance sensors on the vehicle. Now, with this idea of ADAS, one thing that we're really trying to accomplish is what we call sensor fusion and cover multiple zones around the vehicle to kind of create a safe operating zone for the vehicle to live in. And we're going to do this by utilizing sensors such as ultrasonic sensors. These would be our park assist sensors, which are located in the bumpers of the vehicle, front and rear. We will be using cameras, so this would be something like the camera in your windshield by your rear view mirror. And this is going to be able to detect where we're at in the lane. And we also have park assist cameras that are going to be in the mirrors at times, sides of the vehicle, front and rear bumpers as well. And this will give us sometimes our 360 image, if you will, or a bird's eye view as to what it's going to look like around the vehicle when we're parking. Now, some things we need to consider with each sensor also is, how does that sensor operate? And so an ultrasonic park assist sensor is going to essentially just measure distance, and it's going to send out sound waves to an object, and as the reflection of that sound wave bounces back to the vehicle in greater frequency, it now all of a sudden knows, okay, I'm getting closer to this object because the sound waves are bouncing back in a greater frequency. Radar is actually going to send a signal out, and generally we're going to try to cover a further distance than an ultrasonic sensor, and we have different range radars also. So one other thing that a radar does is it can actually measure distance with relativity to the speed of the vehicle. Now, one other thing we're going to be utilizing, of course, is going to be the optical, which is going to be our series of cameras around the vehicle. This will be things like the lane keep assist camera in the windshield or the 360 cameras in the bumpers. And LiDAR is out there for 3D mapping. However, the three that you're really going to see a lot in the shops, and especially our aftermarket shops, will be the first three sensors that we just showed. Now, if we kind of look at a grand scheme of what does the sensor fusion look like and a little bit of a description to these areas, if you look at the different colors, the park assist sensors are just a short range and will be this pink area very near to the vehicle. As we use our radar sensors, this is where we're going to actually be able to reach out a little bit further. We're going to be able to see our blind spots, cross detection in case we're trying to back out of a parking spot. Someone's coming through the parking lot at a different angle. These blind spot sensors can actually measure that. And if we need to actually try to do what we call adaptive cruise control, where we can have the vehicle slow down and adapt to the driver in front of us as we use cruise control, this is what we call our long-range radar. This is a more directional radar, so it's focused on a smaller area. And this is one thing to keep in mind too, is just how critical the calibrations need to be for these systems. So with the distance that this adaptive cruise control radar needs to reach out, if this is off at all by even a couple of degrees, this is a long range off if we are looking at that angle at a distance. Now, I just kind of briefly mentioned at the very beginning that there's a lot of tooling required for these systems. And so I want to show you a slide on what tooling could be required. And so we've got an image here of just some of the very basics at the bare minimum really of what we're going to be utilizing. So we're always going to have to establish what we call a center line to the vehicle. The manufacturer is going to tell us how we have to do that. And so many times what we're going to do is drop a plumb bob at the center of the front of the vehicle. They'll tell us where that measurement needs to be taken, and also the center of the rear. We're now going to have to create a straight line from the one point to the other, and we're going to show in some slides how we actually do that too. So this is at the very basics. We would have to be using a plumb bob, a string or a chalk line, and a series of markers to establish this. This would be kind of the more mechanical method, if you will. If we're using some of the newer systems out, or if we want to try to get some of the tooling ourselves just on an individual basis, we're probably going to be using a series of lasers now. So we'll still use the plumb bob to establish our drop points front and rear, and then we're going to shoot a laser to actually get our straight line over there. Now for measuring tools, we can again go the mechanical method, use something like a tape measure, or we can actually use a digital readout. And so here we've got a Bosch unit, and we actually have it right on the face of the radar, measuring over to our target, making sure we're at the distance we need to be to perform a calibration. Again, we're going to have a series of leveling tools also. So tons of measuring tools are going to be required in order to perform these calibrations. Here's a series of levels that you're probably going to need. One being on the upper right-hand side, we see a very small squared off bubble level. This is going to sit on some radar assemblies to be sure that they are actually sitting level. Once, of course, we've verified that the vehicle is actually sitting level. So once we've done that, this is like the baseline to start the calibration on some radars. We also may need a small torpedo level and an angle meter. So the bottom right picture is an angle meter. It may tell us we need to place this at the bracket of the radar or the face of the radar, and then we're going to have to adjust it to a certain degree in order to then perform the calibration. Now, marking tools. I kind of already pointed out that we're going to be using a series of markers or anything like that to make our little drop points. And what I also would recommend is getting yourself some tape. We're going to put that down about where the plumb bob is going to drop, and that makes a very clear, distinct area to make our marking on the floor. So this is just kind of a tech tip of it's nice to lay out some tape. You can very easily see where your marks are. They don't wipe off, and your marker is going to lay on the tape easy. Now, one thing I like to do if you're going to use the method of using a laser, I would get a reflector as well, and it's got a crosshairs on it in this example. And what we can do then is once we've actually dropped our center point to the front and rear of the vehicle, we can now use the reflector at the opposite end that we're gonna have a laser at one side, a reflector at the other. We're gonna place it at our mark, and now we can shoot our straight line, and we can then go and put our target where our measurement needs to be. So this is a very fast way of establishing our center line in relationship to, rather than just taping down a string, throwing it under the vehicle, dragging it out, and then taping that down. If we've got a reflector and a laser, this can be a very fast process. So this is going to be kind of what that looks like. We're going to have a laser in front of the vehicle in this instance, and we're going to have our reflector near the back at the drop point. So you can see how we used a plumb bob. We established a rear center point, and now we're actually putting the reflector at that, and we're going to line the laser up exactly where it needs to be on the crosshairs of that. Now, in relationship to why do we need to establish such a perfect center line to the vehicle? In this instance here, we've got a picture of what it looks like to do the calibrating of one of the 360 cameras. And so all of these images of the generally like 4 cameras, we have to mesh all of these images so it looks like a 360 bird's eye view. They're not actually, they're a fisheye lens to each one. And if we do not have a perfect center line, if you look at our crosses here for basically our intersection point of the meshing of cameras, if we are off with that center line, we're now a great deal away from the vehicle. And this is really going to throw off our calibration. And when the customer goes to drive that vehicle, they're going to have some blurry lines in between the transition from camera to camera. Now with the camera calibration also, we have to know what they require for a target on there. And so there are times where, in this instance, like a Toyota calibration, they may tell us, yes, you can print off the target. Here are the specifications. Print the target off to this. And if you have it at that specification, then you're going to put it on an approved, backing essentially, put it on the target that they tell you to put it on, and then you can run the calibration. There are going to be other times though where they tell us that we cannot do that. And so now I want to actually go into another thing and actually just show you a little bit on the tooling what a process may look like. And so we've actually got an Autel scan tool set up here, and we want to walk you through the process of selecting the calibration on a unit and what it looks like. So here what we've done is we've actually loaded our 2024 Toyota RAV4, and we've already entered into the area of selecting a module. You may see that we've got the blue highlighted module, and so that's the front radar sensor for adaptive cruise control. We're going to select that module. And once we go into that module, we select OK. And now we can actually go into special functions. And when we go into special functions, we've got all of our different readings of what our options are in order to perform a calibration on the vehicle. In this instance here, we're probably going to have to read the misalignment reading first of the radar if we're going to do a calibration on it. And then we're going to go to what we call the front beam axis adjustment. This is going to be the actual calibration of the radar itself. So once we follow service information, lay the target out in front of it, we can then go to the adjustment, run the procedure, and then we'll check the misalignment reading again after that and verify that the calibration was successful on the vehicle. So with some of that information that we've just covered, let's go into a diagnostic scenario of a situation where we don't necessarily need special tooling, and it's kind of a straightforward process. So you may have heard that you may need a lot of ADAS equipment, and you may need like an Autel unit with the full ADAS package, or a Bosch unit, or Snap-on, anything like that. Well, we might be able to get away without it for some units. And in this scenario here, what we've got is a 2015 Jeep Cherokee, and we've got a trouble code for one of the park assist sensors. Now, in going to service information, we're going to diagnose that. And what we found on the vehicle is that someone replaced a park sensor on there. And when they did, they actually put the incorrect sensor in that location. And so it recognized that the operation of that sensor is faulty, it's incorrect. And so they're going to actually swap it from position to position to verify that that is exactly what's going on. And they verified that it is a sensor issue. Now, they get a new sensor, place it on the vehicle. They've got no trouble codes. Now, are we done? Well, we're going to go back into service information, look on this vehicle, and for this Jeep Cherokee, there is no calibration. And so we can actually take care of this ADAS problem with just a scan tool that can be capable of reading the trouble codes for that system and verifying the data at times too. So for the instance of a Ford vehicle, it's kind of a similar process where not necessarily a calibration per se, but we may need to look at the data of the sensors afterwards to make sure that we're seeing the data that we need. Now, moving on from the tooling that we don't need calibrations for, we're going to actually look at when do we need to calibrate and what's required for that. So some of the conditions that we're going to have for an ADAS calibration would be if we remove one, and this doesn't mean just removing the component. It may be removal of a front bumper. So if you're doing an AC condenser on a vehicle, for instance, this Toyota RAV4 that we have, if we take that bumper cover off and the radar is actually in the bumper cover, we've now just misaligned this radar after we've reinstalled the bumper. It does not sit in the same exact location, and there's a likely chance that that is off by a little bit. And even a little bit with these systems is too far when we're dealing with such a long range to be verifying that we actually can have adaptive cruise control. If we do any types of suspension repairs, which is wheel alignments, replacing ball joints, if we do a windshield replacement, we do a lane keep assist camera calibration after that. If we have a collision, there are several different reasons why we'll have to do different calibrations. And this is where service information will tell us what we have to actually calibrate after a collision. This will include if we have airbag deployments. Now, vehicle modifications, this is a whole other topic, and a lot of the time we're going to still say that we should not be doing an ADAS calibration on a modified vehicle because service information doesn't have the spec for us. And so we do not want to take the risk of calibrating something incorrectly and then having someone have a personal injury fault after that. So generally speaking, modified vehicles are still kind of a no-go at this point. And again, to the point that I just made earlier, if we are removing a bumper for something like an AC condenser or even anything behind there, then we're probably going to have to do calibration of a radar assembly. Now, there's going to be two different types of calibration also. We're going to have what we call either a dynamic calibration or a static calibration. A dynamic calibration is scan tool driven. So dynamic means basically we're going to do something with the vehicle, and so generally speaking, we're not going to have a target required for the vehicle. It's started by a scan tool, and then most of the time we're going to drive the vehicle to calibrate it. Now, a static calibration is going to be completely different. We're going to actually be just in the service bay. There's going to be a target required, and it's performed in the bay, so we now have to follow a lot of space requirement and oftentimes lighting requirements too. So we've got to really be aware of our surroundings when we're doing a static calibration. And that kind of brings me to the point of calibration environment. If we're going to do a camera calibration, I've kind of shown a picture here. This is on a Toyota also, and we're doing a lane keep assist camera calibration. Now, one thing we've got to keep in mind with the different units we're calibrating is how does that unit function? So if we're doing a camera calibration, it is a visual component. It is looking for something. And so with this, it needs to be a very simple backdrop. If we have a really busy backdrop, lots of different colors, tools, toolboxes, everything like that, that may be too busy for the target to be acquired by the lane keep assist camera. And you may also see there's a window there in the picture. However, there's a white blind over it covering some of the light that's coming in. If we have too much light coming in, you may think of looking at your scan tool in the light and seeing that reflection and how you can barely see the screen. Well, it's no different for this camera here, where if we have a lot of light shining on that windshield, that camera can barely see the target. Or if we have backlighting shining on the target, we can run into the exact same scenario. So this would be a great example of a poor environment here, where this Ford 360 camera calibration is actually done with very, very long mats, and they take up a lot of room. Now, what you're going to see here is on the one side of the vehicle, there are some very bright lights along the wall, and they almost are washing out the target on the driver's side of the vehicle. This is going to be too bright for it to actually calibrate properly. And on the right side, it's going to be hard to see in the picture, but there's actually a grate to the middle of the vehicle here. So the vehicle's really not centered to a level surface. And also that target has some wrinkles in the middle. This is a failed calibration and actually does not pass. So we're going to have to find a really large level environment, and the lighting has to be even around there. And this is something to think about for if you're going to get into ADAS calibrations, is do you have the space required for some of these static calibrations? Now, earlier I talked about that center line to the vehicle and how critical it is. I've got the camera calibration actually shown on the center display of a Toyota, and I want to show you what that looks like with those crosses there. So when we're calibrating that camera, we're going to adjust that fish angle or wide angle camera so that they mesh properly going to those crosses. And so this is going to be where we actually just adjust the scaling of this camera so that it meshes perfectly with the side ones. And then we have what looks like a good 360 image, only because we're meshing all of those camera angles. Now, one other thing that I'd always recommend when we're doing any type of camera calibration is to verify it afterwards. And I go through a series of drives after calibrating the vehicle, and I'm going to drive straight into a parking lot. I want to make sure that when I'm rolling through, those lines stay true and that it doesn't all of a sudden start kind of swaying towards the front or back and kind of kicking out as it goes away from the vehicle. And then I also like to go perpendicular to the parking lines and also make sure that the lines aren't like staggering when I'm driving along. If it is, I may rerun the calibration. Now, we're trying to cover a lot of information in a very short period of time, so I thank you guys for kind of sticking with some of this, and we're going to go through another case study. So we kind of went through a lot of the camera calibration things, and now we want to look at what does it look like when we do a radar or short range radar calibration. Here we've got a 2015 Toyota Sienna, and the work order for this is that the left-hand blind spot module, so there's actually a radar assembly in the left rear of the vehicle for detecting blind spots, and that was replaced after a collision. Now there's a message on the dash stating that we need to check the blind spot monitor system. We verify the customer concern and we agree there's definitely a message on the dash. There's something wrong with the left rear blind spot. So the technician begins by just performing a visual inspection. This came from a collision shop, and they put the rear tail light assembly back in. Looks like it was a good repair from what we can tell. So we're going to keep rolling with diagnosis. And now we do a scan of the system, and we come upon a slave module beam axis inspection incomplete. Now, I showed you just a minute ago on the Autel unit that even on the front radar, they call it the beam axis. And so essentially that's the calibration, or in this case, the inspection is that we didn't actually run the inspection utility of this blind spot module. And so the beam axis inspection has not been performed. So this is a function of the scan tool. We need to actually perform this. And so we're going to select the left-hand blind spot module, which in this case, from service information, is the slave module on this one. There is different vehicles, there are different vehicles where this is actually a different situation. So you may have it where the right-hand blind spot is the slave module. So we're going to run the beam axis inspection. That should get rid of our trouble code. However, that is not calibrating this vehicle. So we are going to run the inspection. We're going to look for the target, and then we're going to calibrate the blind spot module. Now, earlier I said how a camera needs to have a perfect visual around the vehicle. With a radar, we need space. We need open area where we have nothing in the area. If we have a hoist, a vehicle, anything like that, that radar is going to pick that metal object up, and we are probably going to have a failed calibration, or we might actually pass and be picking up the incorrect object. So we want to have this open area. Service information is going to tell us how much we need behind the vehicle, and we've got to have that open area. Now we're going to take a stand, which is what service information will tell us we need to use, whether that's our Autel stand, our Bosch, Snap-on, anything like that, or if we use OE tooling. So whatever it is, it's got to match the specifications we need. And now we're going to perform the inspection. So we're going to actually run that utility to try to get rid of that trouble code that we saw earlier. So essentially what we're doing with that calibration is we're going to put the target out of the inspection area. That open area that it told us we had to have, where basically that's where the blind spot module can detect something. We want it just out of that, and we want to make sure that it doesn't see it. So with the target out of the area, we verified, okay, the indicator's not on, meaning that the target is not seen, and that's a good thing right now. It's not seeing it in the inspection area. The technician now moves it into the inspection area, and we want to see, does the blind spot indicator come on? We've now verified that it does come on. Again, that's good. We should have cleared the inspection out of there. And so we scan the vehicle. Again, the inspection is out of there. So this means we don't have trouble codes, but we actually did not calibrate this vehicle yet. So now we're going to have to set up the target in the area that it needs to be. And then we're going to run the display, essentially seeing where the target is, make sure it's okay, and then adjust or calibrate the blind spot module. There's a lot of prerequisites for actually setting up this area. Again, we need to have that open space for the blind spot target. We've got to have nothing metal in the area and just an open area. So this is not about lighting with radar. This is about having the space we need so that we don't detect objects. Service information is going to tell us exactly where to place this target. Now, I will say too, there's a couple of things to this. If you're using OE methods, there's actually a service bulletin for Toyotas giving you a blind spot calculator, because it may give you only the 3,286 millimeter measurement, and that's a really hard measurement to come up with if you're trying to calculate all of these different measurements. However, they have a PDF where you can enter all of these numbers, and you can just measure straight back off your center line and then measure directly over to the side, which is a much easier way to measure it out. If you're using one of the aftermarket tools, something like an Autel or a Bosch unit, they're going to actually give you the right angle measurement right over there, so it's a little bit easier. We're now going to start the axis display selection. However, it looks like that we actually had a failed detection on here. And so it looks like we might actually still have an issue with this vehicle. So we've got to think here. Well, we've tried the calibration a couple of times now, or the inspection a couple of times, and it's not detecting it. Well, we had collision repairs to the left rear of the vehicle. So we're going to have to take a closer look at this. We're going to ask the shop to pull that bumper again. And now we've got to kind of figure out, what do we have going on? There's not really a lot of specs on this situation. Well, we have a right side of the vehicle that is going to be perfectly okay. So how about we go to the left side of the vehicle, measure some of our inspections that we've got on the vehicle, and see what we get on the right side. So we go to the left side of the vehicle first, which is our problematic side, and we measure 3.3 degrees on that radar. Going to the right side of the vehicle, we're at 0.3 degrees. So it looks like we've got a 3-degree difference somehow between these blind spot modules, and we've got to figure out why there's a difference. Well, if we take a little closer look at the different blind spot modules, the left hand to the right hand, and we look at this mounting, if you look very closely, the left hand side, the plastic bracket that goes around the blind spot module is actually mounted behind the module. And so this is actually what's kicking our module off a few degrees. If you look at the right-hand side, you can see how that's supposed to actually surround the outer area of it. And then we're going to bolt the blind spot module behind it. So with this, the technician actually bolts it up properly. And you can see now it's inside of the plastic housing. They verify that the specification is the same as the right-hand side. We're now good to go. We're going to proceed with the axis inspection again. So specifications for this module is anywhere from negative 3.6 degrees to positive 3.6 degrees. And we have a reading of 2.9. So we're within specification. And now we're able to check that off our checklist. And the next thing we're going to do is actually calibrate this blind spot module. So we go to the axis adjustment, which is the calibration of it, and it says that it detects it at 2.9 degrees, it measures it, and that we've calibrated it successfully. So this is our actual calibration of the blind spot module, and in this instance, we've calibrated the blind spot module successfully. We can now check all of these things off on our list to do, and we're going to perform an all module scan after that to make sure that we have no trouble codes afterwards and that we don't have any other systems now setting trouble codes. We're good to go here. We have no calibration or axis adjustment or anything like that where we're setting trouble codes. The only thing we have left on this vehicle is to retest after the repair. We want to make sure that it actually works. So this goes with any of our calibrations. If we're going to do a camera calibration, I want to make sure that it can keep it within the lanes. I want to make sure that I can do parking lot maneuvers for a 360 camera calibration. On this vehicle, we verify that the blind spot indicator is coming on for the customer. So with covering that last case study, I know we're trying to really go through a lot of things in a short period of time, and we could definitely go through hours of information on this. And again, I love covering this stuff, so I could probably spend way too much time on it. But throughout this class today, I hope that we kind of learned just a little bit about determining when we need to do an ADAS calibration, what it takes at times to calibrate these different components, diagnose the ADAS faults. So let's say we have a calibration fault or we have a system fault prior to any calibrating. Well, what was the cause of that? What do we have to do to remedy that? And what tooling is required? Also, we did analyze a calibration failure on that last case study. So we got to see one actually fail and what it took to remedy that. And that was covered with a couple of different case studies. And we actually saw an example too, where with that Jeep or a Ford situation where we actually don't need an ADAS target or anything like that. We can use a scan tool in certain scenarios. And so with that, I thank you guys very much for attending today's class. And I'm really glad that you're able to join us. And I hope that you're able to use a lot of these skills and different tips and techniques in the shop in the near future. So thank you very much for attending.